All right, everyone. Welcome to the Data Science Seminar from the University of Washington eScience Institute. As part of the University of Washington, we acknowledge the Coast peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Macoshut nations. Our speaker today is Maximilian Puel-Matuzel, Research Associate at MILA at University of Montreal, working at the intersection of data science and human behavioral sciences. He develops theory and data-driven models across disciplines and scales of biological systems. Max earned degrees in math and physics from the University of Toronto and a PhD from the University of Göttingen. The title of today's talk is Topic Correlation Networks Inferred from Open-Ended Survey Responses Reveal Signatures of Ideology Behind Carbon Tax Opinion. I would like to make an announcement. There will be no seminar next week. Enjoy the week of Thanksgiving. Please use the Q&A feature of the Zoom webinar version again to ask any questions at the end of Max's talk. And with that, I would like to ask Max to begin his presentation. Thank you.
Great, thanks Nicoletta for organizing, and thanks your institution for the opportunity to talk today. So I'm a bit under the weather, so I apologize in advance if I'm a little more lethargic than I am usually. So this is not really my day job, this research topic, but it's a topic that I've used to get me into what I think is a really important field that I'm excited about and that I'd like to sort of try to transmit some of the excitement today. This is work joint with Eric Lachapelle, who's a professor in the political science department at the University of Montreal. I approached him earlier this year wanting to sort of work in this area, and we've been sort of working together based on a paper that him and some other researchers put out this year in Nature Climate Change, which I'll get into. The title is a mouthful, but let me just get into the motivation. So I guess probably many of us don't need a reminder that our civilization is in a climate emergency. So on the left here, you'll see an image of the sun heating up the Earth every day. And there is heat that escapes out into space, and there's a difference in those two, and that difference is going up because we've found a way to couple our industrial our industry into this massive energy system via greenhouse gas emissions. And so there's a sort of established plan to try to handle this issue. So this involves, this is a nice graphic that I think sort of simplifies what success would look like. So climate impacts are on the y-axis, time is on the x-axis, and the red line is sort of what would happen presumably if we did nothing. And we kept pumping out CO2. So the first step is to cut greenhouse gas emissions. And that's what the black line shows. But there's already quite enough in the atmosphere, and it doesn't come out readily. So we'll need to develop technologies to bring it back down. That's what this green part is. But that's going to take some time to develop these technologies. And so in the meantime, we'll probably need some other approaches, but let's just focus on the emission reduction. So this involves sort of huge projects such as developing a renewable energy sector, stopping new fossil fuel developments, and likely reducing overall consumption and energy use. And all three of these, I'd like to emphasize, have really important social dimensions, that it's not just a technical problem of developing technologies, but really I think changing the way we think about who we are and what the goals of our society are. And in this pursuit, I think I see an important role in stewarding the public perception that we have about where we are and what are the solutions going forward, that I think demands a level of sort of scale, not unlike some of the other large scale sort of information monitoring enterprises of the past. So this is a particular example that you may be familiar with in World War II. There were in Bletchley Park, they were sort of tasked with reading German intelligence and sort of really getting trying to construct a sort of information landscape that was favorable to winning the war. And I think there's a similar sort of idea here of what we need to do for climate change. Effectors in this stewardship system would be, designing online platforms for better discourse, less misinformation, getting collectives, groups of people embedded in communities, their own communities who care about this problem to become active, and also, I guess, push communication campaigns that are effective. And I see all of these things as being supported by something that I guess could be called social analytics, for lack of a better term, that can support those efforts. And so today I want to talk about this idea of stewardship, but in the context of transition policy. So in a policy design process, so I'm not at all a policy analyst, but the process is policy is designed, it's deployed, measured. Maybe its effectiveness is measured, which could be measuring what the public opinion is, so what people think about it. And I'm sure there's lots of other things that could go into this list. And there's some iteration process, ideally, that improves the effectiveness of this policy. And so today, what I want to talk about is this one line here about measuring public opinion and trying to figure out why people think the way they do about a given policy. And I think an important backdrop to consider when thinking about this is that there seems to be there is a sort of growing polarization of the both the climate discussion in particular, but more generally, and these the ideologies behind that's driving this polarization and the structure of various aspects of our society that are driving it are important things to consider. So today I'm going to talk about public opinion of carbon pricing in Canada. That's the work that Eric does. And I'm going to frame it in the context of a case study in ideology-driven policy opinions. So what is a price on pollution, which is what you'll hear when liberals or progressives talk about it, and you'll hear carbon tax when conservatives or more right-leaning people tend to think about it. So in Canada, it's specifically this. It's some policies. I mean, there's a federal program. It's extremely complex. I'm not going to get into it, but basically the idea is that polluters pay. So there's a price tag on each ton of CO2, and it's slated to go up year by year. So for instance, like if you go to the gas station to get gas for your car, there's a small tax that you pay on each gallon of gas that you buy. So it's in principle not progressive in that it doesn't scale with how much you make. So there are additional programs like a big emitters program for industry. And in fact, there's a rebate program that sends back what's earned by this tax back to citizens, such that 8 out of 10 households in Canada actually come out ahead with this tax. Economists agree mostly that a price on pollution is a useful and perhaps the sort of best economic instrument that we have to institute emissions reductions. But publicly, its popularity is extremely low, typically also drastically different along political lines. This is a quote from our current Conservative Party leader that said, "Technology, not taxes, is the way forward to reduce emissions." So this is the sort of backdrop that led Eric and some my collaborator and some of his collaborators to publish a paper this year in Nature Climate Change, where they wanted to assess the carbon tax, and in particular this rebate program, which I'll get to on the next slide. But just to show you some sort of quick results from that work. So they recapitulated the result that the support is quite low. So here, all regions except for Quebec have less than 50% support. And if you break it down by political party, you find that it's tried, and that conservatives have quite low support, while liberals are quite high. So in addition, they did an interesting intervention where they asked people, they took a subset of the survey participants, and they got them to estimate how much they think they got back in this rebate program. And the estimates are listed here in this column on the left, where the green is the estimate that they actually got, and the value that they actually got. So on the bottom here, you see the x-axis goes from $0 to $1,000, and the black bars give the counts. So we see that most people underestimate the amount that they get from the rebate. So then they went on to a next step and said, okay, well, let's just show them what they actually got, and see if they update their beliefs. And the answer is no. There's absolutely no change when they are told that they what they get back, which typically is larger than what they estimated. So that doesn't seem to change. And that's actually not irrational if they have a really strong prior that, you know, taxes are sort of not a great thing. Showing them that they get back more money isn't sufficient if this prior is sufficiently strong. And that's something that you can show quantitatively as being a rational sort of outcome of Bayesian probability mechanics. And so then they actually got them to through a scoring process. They computed a proxy for the subject's belief that they thought they lost out, and it turns out that telling them that they made more actually tended to decrease their belief that this was a useful tax, and that they didn't actually lose out. So it increased their belief that they were losing out. So I think what this shows is that it's really not just about showing people more data, because these people are coming in with strong beliefs, and if we don't address those beliefs, we're not going to make much impact. This is a result, I guess, that's probably been recapitulated in many areas. Okay, so if beliefs are so important, how do we study beliefs? And in particular, I guess, the ideologies behind why people do what they do. So ideology is sort of a complex concept, but let's do like a simple example. Here is Frank. He has ideas about how the world works and who he is, and in a sort of natural science view of the world, these ideas exist as patterns in his brain, and these patterns are shaped by the patterns, by the similar patterns in other people's brains, each of which are slightly different, but they have some common grounding. And it's that common grounding that I think is the object that of interest here. So a sort of person type condition distribution over a belief network about the world. And this belief network is obviously going to be very interconnected because the things in the world are interconnected. It's going to be highly dynamic. It changes over time as people experience things in the world and change their beliefs. And it's not going to be sort of a simple optimization of coming up with one objective like maximizing economic benefit or something. There's lots of complicated things that would go into such an object. I've written it here as this sort of interconnected graph, but it's not even clear that that's a sufficient representation for what this physical basis of ideology is. However, it is expressed in what we collectively say and do, and I think that makes it a empirical object, or at least it means we can start to devise empirical methods to test it. We can sample it then by getting people to do surveys, as the work that I'll show here is about. But we can also, track people's activity on social media or other types of forums that allow for quantification of what people say. So let me just, this is the data set from that paper, which is where I'll be getting the data that I'll talk about today is, where importantly, they asked people to elaborate on their support or opposition to the carbon tax. So these were open-ended responses, but in addition, they got lots of metadata about who these people were. And I'm going to analyze it today through something called a bag of words approach, which is where you sort of throw out all the grammar and the syntax, and you just look at sort of what's talked about and in what amounts. So just to give you a first pass through the data set, so these are the histograms of how many people supported and opposed. Here are the word frequencies used in the responses over the support and opposed groups. The support group just tends to have a sort of relatively flat, whereas it's clear that opposed, there's one big word that's talked about a lot, and I'm sure you can all guess what it is. It's the word tax, because if you oppose a carbon tax, chances are it's because you don't like tax. Whereas the words used in support, in justifying subjects or participants' support of the carbon tax are sort of much more diffuse. They talk about lots of different issues. Now, given that we have all this rich metadata, what are some things that we can look at? So, we can just plot for each metadata cohort. So, for instance, on the left here, I've looked at different age groups. So black to gray is going up in decades, and so as people age, apparently they support a carbon tax less. So sorry, x-axis is support is the fraction of people of that metadata group that supports carbon tax. The y-axis is the subset that oppose. So that there's this shifting with age, but of course there's also this shifting, and in fact an even larger shifting with partisanship and also with party vote. So you can do the same thing. So that was for the 2019, which is pre-pandemic data set, and 2022 is this year. And you don't see very many differences. So this is sort of consistent. Maybe the one thing here is that there's the youngest group now supports climate change more. That's a small group though, so I doubt it would be statistically significant. So things are relatively stable. In this 2022 data set, they actually also asked what people, which of either natural or human causes they thought climate change was a result from. And so it's clear that if you think humans are causing climate change, you're more likely to support, whereas if you think it's from natural causes, you oppose. Okay, so it's clear that there's just from the word statistics and who these people are, and the tax is a loaded word. Here's a plot that I showed up of people that were of a paper in which they showed people two products and showed that the costlier one was because there was either a tax involved or an offset. And with the offset, people didn't really seem to mind. But if you call it a tax, as you move from Democrats to Republicans, you really get a drop off in support. So tax just alone as a single word is a big deal. But that can't be the whole story, right? There's a reason why tax is the important word that it is, and that recruits a much more complex, probably system of ideas or an ideology again around opposition to a carbon tax. So in this talk, I want to go beyond word usage and towards generative modeling to understand the language that how these metadata types drive the language used in justifying support or opposition. So topic modeling is the generative modeling tool that I'll talk about today. It involves a vocabulary, and then a topic is defined as a distribution on a vocabulary. And just since I'll be bringing it up a lot, there's this way of representing a distribution or things that sum to one in what's called the simplex, which is where each side corresponds to the probability. And so for a given distribution, you can locate it as a particular point in this triangle space for the case of three, a distribution over three outcomes, but in higher dimensions, it's this higher dimensional object. That's called the simplex. I'll be referring to it. So if we have the sort of the in words, oh, and I should say that the vertices of these are where the distribution is completely centered on that one. So with probability 1, you're at that event, and 0 everywhere else. So a topic as a distribution on a vocabulary is a point in this space where the usage would be of the other words are on the vertices. Now a topic mixture then is a particular point in this simplex place where now the vertices are the topics themselves. And this would be a particular way that a subject would mix topics. And we can set a prior on that, so a distribution on that space. And so this is a generative model. So the way that the model generates a response is that it samples a particular topic mixture given the particular prior. It samples a given topic, and then it samples a word given the usage frequency, the word usage frequencies or probabilities of that topic. And so and then you put the word in the first slot, then you repeat the last two steps, and you get a sequence of words, and that forms this response. So I don't have time, I guess, to go into maybe too many details about the model, but suffice it to say that there's 20 years of development of this field. The first and still widely used model is called latent Dirichlet allocation, because it sets a Dirichlet distribution for this prior over topic mixtures. That's been generalized in various ways. One way that is to allow for correlations, for controlling the correlations among the topic mixtures, so that you talk about certain topics, the topics are talked about in correlated ways. So here, this sigma is a covariance matrix parameter. So this is a parameter of this prior, so you have to infer it from data. X here is the mean. The model that I'm going to talk about today is one in which I'll just skip that. One in which instead of having these just be prior parameters, we're actually now going to feed in the metadata. So these are now means, the mean is now going to be structured from the metadata to allow different types of people to have different mixtures. One thing I haven't mentioned is the part of the diagrams on the left here. This is a standard representation of generative models from statistics for those who haven't seen them before. I'm not a huge fan, but they're standard. So here they are. The right side here is what defines the actual topic. So the left is about how you pick which topic. The right is about what these topics are. In the Dirichlet, it's also a Dirichlet that picks the topic. In the structural topic model that I'll talk about today, it's something called the SAGE model, which I don't need to get into. And so there's these three sets of parameters: the covariance matrix, something that scales the mean, and these things that set the way that topics use words. And so this is sort of a Bayesian inference setup here. So we want to estimate the parameters of this model because I should say that this model here is a logistic normal, and the idea is that it sort of leverages the control that you have with a normal distribution, being able to sort of put it wherever you want and add whatever correlation you want is, but map it to the simplex, which is the space that we need that type of flexibility for. But using the logistic normal means we can't do it's not conjugate to the multinomial. And so we have to do something more complicated, in this case, expectation maximization. So we need to find some variational approximation that for the distribution that satisfies this approximate objective. So there's this the authors of the paper that developed the structural topic model really did a lot of from my perspective, quite advanced and useful approximations to make the learning of this model quite fast and have good frequency guarantees, frequentist guarantees. Anyway, so we run it. We can get some topics out. There's different ways to evaluate topic quality. One is exclusivity, which is high when a topic's frequent words are exclusive to that topic. So that's on the y-axis here. The x-axis is what's called semantic coherence, which is high when a topic's frequent words co-occur often. So I've split this up between the types of responses: oppose, support, or not sure. The circles are oppose, say, which seem to have the higher quality, but across a number of topics, it doesn't really seem like there's a single number of latent topics that the model picks out. So how do you deal with understanding a model where there's lots of topics, where you don't know the latent number of topics being used? Well, you look at all of them. So this is just I wasn't sure if I should use the word phylogeny here, because that obviously has very particular uses in population genetics, and I'm sure people have all kinds of complicated methods for doing this. I just did a very simple thing where you link up. The top row here is just a model with 2 topics. The second row is the model with 3 topics, etc. And I just linked topics back to their parent, to the topic in the parent model that's closest in this vocabulary space. So that's one way to look at, that's one way to look at these how the model behaves over different topic numbers. We can compare these over different years. It's not sort of salient what's sort of different. We can sort of look at branches. So here, this branch, and here, this branch, say. So this one from 2019 talked about alternative energy, and here's a sample topic. With so many alternative sources of energy, we should no longer be as heavily reliant on these non-renewable sources as before. whereas in 22, it seems like the topic that's sort of dominating here is about affording and sort of more cost of living. So Canada's carbon emissions are insignificant compared to sort of China. And so I don't support a tax. So thinking about what the topics actually mean can be a little bit fraught because you don't get told what the topics are about. You just get the list of, most of words that are sort of most contributing to those topics. And so interpretation can sometimes be a bit tough. There is a way around that I pursued, which involves getting into the latent space of the model. So let me talk about that for a bit. So given that we've learned the parameters of this model, we can compute the most probable topic mixture for each response. So remember, we started with this prior, but now that we've done the inference, we can talk about posteriors. And so each response can now be represented as a point in this topic mixture space. And we have that for all the responses. So what we can do is use the metadata and look at the subsets of this data cloud that correspond to different types of people. We can take that data cloud, do some, we can do statistics on it, look at a covariance matrix of their mixtures, and for instance, produce visualizations like a correlation network between these. So this represents the way that different topics are correlated with each other. So here would be that there's sort of two groups of topics that have some correlation. And so the question that we want to ask now is like, what is, how can we analyze the statistical structure of these clouds in this topic mixture space? So one way to sort of think about it is to think, okay, well, like are these mixture spaces actually useful? And so one question is, can they predict the metadata? So I just took a linear classifier on these data clouds. And so, for instance, here what I'm showing in this row of scatters is the first two principal components of a projection of the data, where I've colored the data, in this case, based on oppose or support. And so just visually, you can tell it's very well separated. And you might say, okay, well, I mean, oppose and support are the sort of dominant differences because that's what people were actually told to talk about. And so, of course, they're going to be well separated in this mixture space. But because there's so many things that are correlated with oppose or response, many of the metadata covariates also can be discriminated basically perfectly. So the reason you don't see any lines here is because they're all at one. So, I mean, this is a big space, and there's this typical approach to better classification of mapping into higher dimensional spaces, but nevertheless, this shows that the space is sufficient to, for instance, classify between left or right leaning or progressive or conservative, and that the directions of maximal separability between the values of the metadata classes aren't just in a single topic. So here, what I've shown is just the projection of the components of the sort of first principal component, and although there is, topics that do contribute more than others, it's not like there's just one. Okay, so looks like I forgot to do the slide animations here, but let me just move on to the next part, which is that I wanted a means to analyze these data clouds that didn't have to refer back to the topics in any way. And so just geometry is an interesting set of metrics to develop. And so there's four, I think, that are of relevance here. So and in fact, I think are sort of the four principal ways that you can distinguish a unimodal data cloud. So first is just the size in this simplex space, which in this case would correspond to how heterogeneous the responses are, right? If the data cloud over a subtype is very tight, it means people of that type tend to mix topics in a similar way. Whereas if it's very large, then people tend to sort of are more heterogeneous. The second metric is just the location of the data cloud in the simplex. So if it were centered at the very center, it would recruit topics equally. And so one metric to look at is just the distance to the center, which you can compute by just like the entropy. So that's 1 at the center. When it's normalized, it's 1 at the center and 0 at the vertices. The third metric I looked at was in eccentricity. So this data cloud can have a certain can be squashed in various directions. And to compute that, I took the intrinsic dimensionality, which is a function of the eigenvalues of the covariance matrix, and behaves in some nice ways. And then finally, you can have a squished blob, but where is it pointing? So that's another independent measure. And in that case, I looked at the fraction of positive pairwise correlations, which is sort of how topics recruit other topics in a positively correlated way when for a given metadata type. Whereas, for instance, the eccentricity is more that how much of the dimensions of the volume are being used by a given amount of correlation. Okay, so we can compute what these quantities are across the different. So in this case, I just did the support and oppose. Actually, I included the third not sure field. And so for the volume, we see that the oppose is drops. So so from left to right are the number of topics assumed in this latent space, so the dimensionality of this simplex, and across different latent dimensionalities, we see that the oppose responses are somewhat smaller, which means they're less heterogeneous, which means they're sort of potentially, more. There's a less variable narrative being told. That's the sort of generous interpretation. Moving on to the second column. So this is how much topics, the degree to which topics are recruited equally, or whether there are sort of specific topics that are important. With this particular distance measure, it doesn't seem like there was much difference, at least on the scale. I did do this plot with error bars from sampling from the posterior, and the error bars are quite small. So it's not that it's a statistical problem, but still, I think there probably could be better distance metrics. Moving on to the third column, which is how eccentric this data cloud is. And here we see again that the oppose responses seem to fall slightly below those of the support, which means that they take up a smaller amount of dimension. So the correlation is sort of flattened into particular directions, so that oppose responses tend to talk about similar things. or tend to recruit multiple topics jointly, or mix in fewer ways, I guess is another way to say it. And then finally, there's the notion of where the correlation is pointing, which I quantified by this, how many positive pairwise correlations there are. And again, we see that the opposed responses seem to initiate more positive correlation over most of the range that I looked at. And so the idea here is that they're recruiting, or they're the way in which they recruit topics seems to be sort of mutually enforcing, and that they recruit a set of topics that are positively correlated with each other more so than support responses. Okay, so let me talk, since this is sort of a field that I'm entering in, and I think it's interesting to talk about what the potential is, I guess. So the researchers that developed this structural topic model actually also wrote a book that just came out recently called Text as Data, a new framework for machine learning and the social sciences. And this, along with sort of other research fields that have been developing over the last decades, I think sets the stage for the possibility of a very quantitative and potentially useful in an applied context version of I mean, not that social science hasn't been useful so far, but to sort of scale up the approaches in a way that I think up to now hasn't really been possible. So the science can involve data streams of various sorts. The models are going to be multi-scale insofar as they can be structured at different levels, so the level of the single person or collectives. And here I think there's an interesting interaction between, what I guess I would call sociophysics, although I feel like that term isn't really a great name for work that a lot of people do, but it's sort of these sort of physics-inspired collective behavior models that I think. So I think the physics of collective behavior has developed many of the concepts that we need. It's just that they haven't been ported over as widely or as with sort of enough momentum yet. And I think so. These typically are purely models. They don't often interact with data, but I think with the potential of coupling them or marrying them with sort of function approximation approaches, where we take the components that are sort of difficult to model, and we fit in some neural network component to fit from large amounts of data. I see these sociophysics-like models potentially being quite useful in an applied context. This is going to need a lot of data ingestion, so needs to be sort of informatics infrastructure involving pipelines for nowcasting and data management. There's obviously going to be lots of theory, and this is an enterprise, I think, that would demand input from expertise from a variety of different fields. I didn't have enough time to really work through the policy implications here, but obviously, potentially understanding people's opinions mean that you can better devise communication to support policy. I think it also is a response to this realization that we have all these online platforms, but no one has sort of designed what they're doing to our social systems, and so this is maybe a way to start doing that, and that's important. And ethics is also going to be important here, and I think science can play a role in positioning that debate in a scientific field, or in a scientific forum, rather than in a private forum that these large companies are probably going to be developing in any case. So I'd like to acknowledge some people that advised us. So Mato and Catherine were on that Nature Climate Change paper, and they've been helpful. And Danya Sridhar is a new prophet, Mila, who's worked in NLP a fair bit, and I've been talking with her. And I'd also like to thank Rena, who it runs the Canadian Excellence Research Cluster at McGill on autonomous AI that I'm funded under. So with that, I'll stop here and take questions. And thanks a lot for listening.
Thank you, Max. That was really great. I really enjoyed your presentation, and we are scientists. We live in our ivory towers, and I'd love us to be talking more with stakeholders and policymakers. And your research is really a good example of a work that could have, like you were saying, implications for policy. Is this moving forward in terms of, yeah, these are the results from this study, are, in what way do you see decision makers using this data in terms of communication and other things?
Yeah, I mean, I think now, so with regards to communication, so one specific application of this work, so I should say that these are sort of preliminary results, and I think there's a lot of validation that still needs to be done before they move into a policy realm. But if this result holds up, that conservative ideology behind, or opposition, the ideology behind the opposition to carbon tax seems to be this sort of more worked set of beliefs and ideas, which I think is an attractive or an interesting hypothesis to pursue, that has this sort of highly correlated, that it's not just one idea, it's not tax is bad, it's this sort of network. So I didn't give you a sort of list of what these topics are, but if you look at them, you can see various, like cost of living, unfairness, for instance, to business. There are these sort of particular sort of meme-like things that pop up that are obviously have some sort of network structure to them. And I think currently one strand of communications research says, people are overloaded. You can't give them, too much content. Pick like the most important thing that you think will impact them and tell them about that. What this work shows is that given that there's so many of these ideas that are connected, if you just try to intervene on one, my guess is that there's going to be some effect where the neighborhood just swamps it back out because there are these strong correlations. And so what this might suggest is that maybe instead of putting all your cognitive load budget into one topic, you spread it across the neighborhood of topics such that you sort of lower the tendency for the neighborhood to sort of push back and revert the intervention that you made. So that would be one potential sort of contribution to the communications field if it was validated and sort of seemed to really be the underlying explanation.
Yeah, thank you. There is a question.
Yeah.
Do you want to take it?
Sure. Yeah, thanks, Gregory. So he says, a very interesting presentation. Reminds me of a series of ballot initiatives in Washington. The carbon tax, and it failed. There's a long history of failed initiatives, especially in Canada. So they revised it, which was a carbon fee, right? So changing tax to fee. And the money, instead of being used as a tax, would go specifically to investing in green energy. It fared better, but still lost. Yeah. So, I mean, I think in the United States now, there's this really interesting sort of situation that this giant Inflation Reduction Act got passed, which sort of set renewable energy up for that's gonna establish the field, at least from what I've read. So Mato actually has contributed to a debate in the political science realm that argues that it's actually not about setting the right tax amount, but by satisfying the sort of conflicting interests, industrial interests within each domestic player. So it's not so much these international collaborations, but domestic governments figuring out who sort of cares and has interests and trying to balance those. And that's people characterize this Inflation Reduction Act as a successful example of that approach, because they also gave big oil a lot. And you can argue, the degrees to which that's good and bad. But yeah, there are these different approaches to getting policy passed, and I think it's an interesting. There's interesting game theory work on these. There's actually a competition now that Salesforce is actually doing in collaboration with Mila on developing negotiation protocols. So that's something that we've been thinking about. Thanks for your question, Gregory. I'm not sure. I guess it was more of a comment, but interesting nonetheless. Thanks.
Well, great. There's no other questions in the Q&A, but quickly, how is this translatable to other big social constructs, like a single-payer healthcare, for example? And I think that's the last question for today, and we'll wrap it up here.
Yeah, I mean, I haven't looked at that topic at all, but again, I mean, you just have to run a big open-ended survey study and turn the crank, basically. I mean, I think I'm trying to contribute some more detailed analyses that maybe wouldn't be so obvious from a statistician's point of view. So I feel like the people that developed it come more from a stats and social science background, and so there's lots of useful tools for calculating statistical effects of things. But I think coming from more of a physics background, I take a more sort of systems approach, and so I think I'm asking and interested in slightly different questions, and hopefully we can sort of expand the space of methods that topic modeling uses, and that these can then be used on a variety of questions.
All right, thank you. Thank you, Max. No seminar next week. Enjoy the holidays. Thank you. Have a good night.
Thanks a lot.